In the last lecture, we looked at the well stirred furnace model, in which we treated the entire furnace to be at a single temperature, and we were able to relate the furnace efficiency with the firing rate. And we saw that as the firing rate increases, the furnace efficiency decreases. And although this is a very simple model with several assumptions, one of them is that there is only one temperature for the gas. Then we had assumed a gray gas, and we had neglected convection, and hence you may wonder whether this kind of simple analysis has any value. You must remember that this simple analysis only to get an idea of what are the major parameters which affect the efficiency of furnace. This is not meant to give accurate values of a real furnace. This can be thought about the teaching tool to give you an idea of what the important parameters are. Today, with the availability of high speed computers, you can always do a much more complicated analysis, which will be an extension of this really, and get the more accurate answer. But those computer simulations will not give you any physical insight, will not tell you exactly why this is happening. So, you need these simple models not to give you accurate answers, but to give you an idea about what are the important parameters which influence the furnace efficiency. To illustrate this point, this is a typical power plant furnace, and the region which we were modeling is this portion, so called the radiant section of the furnace, and we treated this all at one temperature, which is not true. There is a large gradient between where the flame is to where the gas are going out, and we will see how to correct for these kinds of differences. But the point about this analysis is not to model this furnace accurately. The whole purpose of this model developed by Professor Hotel is to understand the relation between efficiency and firing rate for a large class of furnaces, because there are many furnaces which are quite different from this furnace, and the analysis will tell you. So, let us now look at the result we got in the last lecture. So, we had the reduced firing efficiency on the y axis and the reduced firing rate or firing density in the x axis, and for various values of the sink temperature, non-dimensional sink temperature, we saw the efficiency was going down. Now, the reason why this result is so important is because in the single chart, single figure, we are able to show where the different furnaces exist in this two-dimensional representation. For example, A is this region, it is the radiant section of cracking coils and oil tube stills used in refineries. B is the domestic boiler, which is used in many houses in cold countries to heat the houses. C is open hearth furnace used in metallurgy, this is this region, and finally, soaking pits also used in metallurgical applications right here. So, 4 different kinds of furnaces here are all represented in a single chart, and it helps us understand why the soaking pits and domestic boiler are having a much lower efficiency than let us say the oil tube stills, which are higher efficiency. And it also gives you an idea of what is the highest achievable efficiency. The highest achievable efficiency at any firing rate is when the sink temperature is very, very low. So, you can see that at low firing rates, the highest achievable efficiency is of the order of 60 to 80%, and as you go to higher firing rates, your efficiency does go down, and at firing rate here of the order of 2, you can see efficiency as low as 20%. So, it gives you a very good handle on the important design issues that we are dealing with, and as the cost of fuel goes on increasing and we need to make the furnaces more efficient, it shows clearly there is only one important way you can increase efficiency, by reducing the firing rate. We have not much control over the non-temperature sink temperature, because that is determined by the application. So, in some application the sink temperature will be quite high, in others it will be low. So, this is not a parameter under our control, but the firing rate is under our control, because for a given flow rate of the fuel that is required, you can have a lower firing density firing rate by increasing the area of the sink. So, that is a design parameter which we can alter in the design stage. So, in the design stage, if we are trying to increase the efficiency of the furnace from somewhere here 30 to 40% to 20 to 30% to 30 to 40%, can clearly see that we have to almost double the sink area, and one has to work out the economics of this issue. So, these kind of simple models are very useful to make broad judgments at the design stage, but finally, after the design is finalized, the actual calculation of the furnace efficiency will have to use a much more elaborate and complicated model, and today that is possible because of the availability of high speed computers. So, we can easily extend the simple analysis that we presented here to more complex situations. We will discuss that in today's lecture. Before we do that, we want to highlight some issues related to this analysis. Now, the first question that must bother you is as regards the assumption of gray gas. Remember that we had spent a lot of time explaining that the gray gas assumption is very poor for most situations, because the gases that we deal with have an absorption coefficient which varies very, very strongly with wavelength, and hence we should not make a gray gas assumption, but we began with a gray gas assumption. So, it is worth asking what is the error that has been introduced here by making gray gas assumption. So, the key point of the assumption we made when we assumed the gas to be gray is that the absorptivity gas is equal to emissivity. This assumption is not very good. So, question is, what is the error introduced because alpha g is not equal to epsilon g. In this case, we know that for most gases absorptivity and emissivity are not same. So, if you look at this problem and look at the radiative transfer when these two are not equal, our radiative transfer equation will look like So, we had assumed these two to be equal and taken it out of the so this was the non-gray case, and for the gray case which we had assumed, we got, I am sorry, here this is not here. So, we had used this equation in the last lecture, which is not right. We should use this equation, but interestingly, in most application that we will deal with, the T 1 by T g will be less than half. That is, sink temperature typically in the application we are dealing with, which was power plant furnace, is less than half. Suppose it is equal to half. So, if T 1 T g was equal to half for convenience, then you see that T 1 to the power of 4 by T g to the power of 4 is 1 by 16. So, this term is very small. So, although our emissivity estimate was quite accurate from the charts, our absorptivity estimates could have been wrong by 50%, but it does not matter, because the second term in the equation contributes less than or around 5% of the first term. So, even if we make a 50% error in the second term, it is not going to fundamentally alter our estimate of the efficiency of the furnace. We actually saw that when we increase the furnace efficiency from 0.38 to 0.21, the efficiency increase was only 7%. So, any error in the second term in this equation, because we assumed absorptivity to be equal to emissivity, would not fundamentally alter the main conclusion. So, what is clear is that as long as the sink temperature is less than half of the gas temperature, we are not going to make a large error in assuming a gray gas. So, although gray gas is a poor assumption, in this example where the sink temperature is small compared to gas temperature, it did not really make a difference. Of course, there are other applications, as we saw in the previous figure. If you are dealing with situations like where the temperature of the sink is very high, somewhere here, this is where temperature is low, here temperature is high, like soaking pit, there you may have to begin to worry about the second term. Okay. So, there you might want to incorporate the fact that absorptivity and emissivity are not equal. Now, let us move on to other assumptions in the Hortel's model. The other assumption that has been made, which could potentially cause large error, is the fact that treating the entire furnace to be at one temperature. Now, this definitely is not right, because the exit temperature of the gas definitely will be less than the mean gas temperature in the furnace. So, this can be easily be accounted for if you assume that the difference in temperature between the mean gas temperature and the exit temperature divided by adiabatic flame temperature. This is the non-dimensional measure of this effect. You can rewrite those equations we developed last class, and that equation will change only slightly where delta here is this where delta was 0 last time, you have got this delta. The only problem now is that we cannot estimate this delta a priori in a 0 dimensional model. You need an empirical estimate of delta. For example, suppose the exit temperature was 100 degrees below the gas temperature. Gas temperature we assumed was around 1700, exit was let us say 200 degrees lower, and adiabatic temperature around 2400. Okay. So, you can estimate delta from here to be the exit is 1500. So, the 200 by 2400. So, it will be delta will be of the order of 1 by 12, okay, 0.1. So, this 0.1 will not introduce larger, but this can easily be accounted for. So, one can make a correction to our estimate if we have in a real furnace some estimate of how far the exit temperature is different from the mean gas temperature. So, one can make correction, though this is a correction can be easily be incorporated. The next issue that you want to worry about is neglect of convection. All of you are aware that in a real furnace, there is a lot of mixing in the furnace due to turbulent flow. So, you might wonder if that is going to alter the calculations. So, one can easily change that. We can write down the gas to sink heat transfer as the term which we had already included. Plus a term to account for convection heat transfer to the sink, and the interesting point is that we can estimate this term and we know a rough estimate, but we can even redefine our A. We can define this as equal to sigma A star effective into T to the power of 4 minus T 1 to the power of 4, where A effective star will be equal to one plus H 1 A 1 rather A star into sigma A star T g squared plus T 1 squared into T g plus T 1. So, this will give you a rough idea of the additional heat transfer that is coming through convection, and this can be used to correct the estimate. So, this is similar to the way we took care of temperature gradient in the gas. So, these corrections for non-gray behavior of gas, correction for temperature gradient in the system, or according to convection, all can be thought of as minor correction to the 0 dimensional model. But of course, beyond a certain point, these corrections will not work. Now, let me take an example of a furnace. For example, take a furnace, a long furnace like this. This is the direction in which furnace gas are moving. What you can do is you can divide the furnace into many zones and treat each zone as isothermal and apply the well-set furnace model for each, and then link it to the next and next until it comes to the exit. So, this is an extension of the 0 dimension model of Hotel, the well-set furnace model, to 1 dimension, by having series of 0 dimensional models linked together by a common temperature. And later you can see that if you want to treat the real furnace which has 2 dimensions, actually 3 dimensions, you can replace it by various volumes. Each volume is considered to be isothermal, and you can have multiple zones, and so this has happened naturally. So, the Hortel's 0 dimension well stirred furnace model has been extended to 1, 2 and 3 dimensions systematically, and we will discuss how this can be done. We will not get into the nitty gritty details of how it is done, but broadly how this concept can be naturally extended to multiple dimensions. But before I do that, I would like to extend the analysis we have done so far to account for how the furnace will behave if there is ash deposit. This is a common problem in power plant furnaces burning coal. So, the question is, how do you account for deposit of ash in a simple model? Now, this can be done quite easily. Now, remember that we had already estimated heat transfer from gas to sink as this is our model. Now, previously we had assumed the sink temperature as known, but if there is a tube in which the water is flowing or to be heated, and the tube has a certain thickness, and on that there is a deposit of ash. This is the ash deposit. So, because of ash deposit, this temperature T1 will increase, but it is unknown quantity, we have to calculate that. So, how do we estimate? We calculate the heat transfer from the same heat is transferred radiation from. So, we have a simple resistance model. This is the temperature of the boiling water, this is the sink temperature, this is the gas temperature. Now, the resistance to heat transfer here comes from this equation. This one from T1 to Tb, you write another equation Q 1 to B will be some overall heat transfer coefficient times the area of the sink into T1 minus Tb. And in steady state, these two must be equal, and hence you find the unknown sink temperature. So, this equation has the 4th power temperature, this is linear. So, strictly speaking, you have to do this numerically, but one can do a little approximation. This Qg to 1 can be written as so you can treat this quantity as HR, a radiative heat transfer coefficient. Okay. And if you do that, then you are writing HR into Tg minus T1, HR into A star is equal to U1 A1 T1 minus Tb. So, we can now solve for Tb. T1 rather, because Tb is known, the boiling temperature of water, and Tg is known from the other radiation calculation. So, if you do that, you will get the following result for T1. T1 will come out as Tg plus U1 A1 by HR A star into Tb divided by 1 plus U1 A1 by HR A star. This is an approximate calculation. You can do a more accurate one numerically if you want to, but this highlights very nicely what the dominant issues are. Suppose the heat transfer resistance between the ash deposit and inside the water is much more effective than the radiated heat transfer from gas to the ash deposit, that is much more greater than 1. This term dominates, you can say T1 approaches Tb. So, which is the case without really any ash deposit. On the other hand, if this is quite small, then the sink temperature will approach the gas temperature. So, that can be quite an important influence on the efficiency of this. So, we can calculate this, and I am going to show you the results of this computation. This is the result of the temperature of the gas as a function of thickness of the deposit. Now, the deposit that is made on the outside of the tube has two influences on the. So, here is a wall and here is a deposit. So, deposit offers higher conduction resistance because deposit is porous ash. So, first it will offer a lot of resistance to heat transfer by conduction. Secondly, it will change the emissivity of the wall. So, it will change the wall emissivity. So, both these issues have to be addressed. So, in the calculation that is shown here, we have taken two different emissivity of the wall. One is 0.9, which would be the case with ash free tube, and if the ash deposited has light colored, so it will have a low emissivity or 0.6. So, we have shown how as the thickness of the ash deposit increases, how the temperature of the gas leaving the furnace varies for two different firing rates, 0.02 and 0.01 kg per second per square meter. And you can see clearly that by the time you have 5 millimeter deposit of ash, which can happen quite quickly if the coal that is being used is has a high ash content like in India, then you can see the temperature at the exit can go from 1000 to 1700, and this will have a very serious impact on the efficiency of the furnace, because furnace is not able to transfer enough heat to the heat sink, in this case boiling water. So, this clearly illustrates how often you need to clean the walls of the tube to ensure that the ash deposit kept to within about a millimeter or so, because as it goes on increasing, it does reduce the ability of the gases to transfer heat to the sink. So, again we see that a simple model of the kind developed by Hotel has given us a rough guide as to what could be the impact of ash deposit on the furnace performance. So, that is the usefulness of this kind of analysis. But as the problem gets more complicated, and there are more dimensions, then of course, the single dimensional model will or 0 dimensional model will not work very well. Now, let us get to a more complex situation. We look at the full furnace design. The problem is truly 3 dimensional. So, if you think of this full 3 dimensional model, you can see that the furnace is composed of large number of volume elements, as well as surface elements. So, we need to extend the single 0 dimensional model of hotel to multiple dimensions, and this is called the zone model. Now, it is routinely used in furnace design, and let us now see how this is achieved. So, remember that there are radiation exchanges between 2 surfaces, from surface to volume and also volume to volume. There are 3 different, let me put that down. So, there is a surface in the furnace, So, this is surface Si, this surface Sj. So, you have to worry about radiation exchange Si to Sj. Then you have a gas volume here, which I will call as Gi, and there is surface Sj here. So, this we talked about this exchange. This exchange is exchange from volume to surface. We have to calculate that. Finally, you have to calculate volume to volume exchange between one gas element and the gas element, that is Gi Gj. So, we need to define these 3 parameters: surface to surface, volume to surface, volume to volume. So, let us define each of these 3. Now, the connection between what Hotel defined as surface surface exchange is nothing but Ai Fij. We use the term shape factor and found it convenient to define it differently, so that it is non dimensional, but Hotel found it convenient to define an exchange factor, which are units of area. And so, just to remind you, this exchange factor between 2 surfaces is by definition 1 over Ai 1 over Aj cos theta I cos theta j dAi dAj by this we have done already many times. This is the standard definition of shape factor, and you have to of course have e to the power minus absorbed Coulomb times the length scale. So, this is the effect of the gas. Okay. So, this is a quantity which defines the fraction radiation leaving I and arriving at j, influenced by geometry of the problem as well as the gas. These are units of 1 over square meter. Now, let us see how we extend this idea for a volume of the gas to a surface element. Now, here since you have to integrate of the volume of the gas, and of course, you have to integrate of the area of the element, and this part is common for the element j, cos theta j is there and pi square is there, that is common. But what you will do is that you have dAj, and for the gas we have A into volume element. So, the main difference is we have replaced dAi by A times dVi, but A is the absorption coefficient, the Gray absorption coefficient. So, this is a simple extension of the idea of exchanging of radiation between two surfaces to exchange of radiation between a gas volume and a surface area. Finally, we had to have another definition, which is the volume to volume radiation exchange. Here it will be integrated over 2 volume. We will have the gas absorption term, we will have A squared by pi s squared, we have dVi dVj. So, I want you to think about how the original concept of shape factor, which we developed in the absence of gas, can be easily extended to the concept of exchange factor between two surface elements, further to exchange factor between a volume element of the gas and the surface element on the walls, and finally, from volume of gas to another volume of the gas. So, volume to volume exchange. So, suppose you want to write down how much is heat arriving at surface Q, we will sum over all j surface elements and go from Sj to Si and multiply by radiosity difference to get the heat arriving at surface I. Now, how much is the surface I from the volume elements? You go from 1 to m, there are m volume elements and n surface elements, and you calculate this Jk into S I, and this will be Bi minus Eb G of k. So, you are able to calculate the heat arriving at surface element I, net heat to be added to the surface rather, to take into account exchange between surface I and surface J, between surface I and volume element K in the gas. And finally, from the energy balance arguments, so this can be taken now, there are, so our energy balance will tell us J 1 to n surface elements plus the m gas elements has to be equal to area of the surface AI, and similarly taking all n surface elements and interaction with gas elements and also interaction between all gas elements has to be equal to 4A Vi. So, these two equations put a constraint on the value of these exchange factors, and so you can solve for m plus n equation that you will have energy balance, and solve for all the Tj's of surfaces and Tk of gas volumes. So, you invert a matrix really to solve for all surface temperatures and the gas temperatures to get the full solution. So, this is now routinely done in almost all organizations which have to estimate radiative heat transfer in furnaces, and this is a natural extension of what was discussed in the last two lectures with reference to modeling radiative heat transfer furnaces. So, today with the availability of high speed computers, one can do, for example, you can divide the surface of furnace to 100 surface elements and maybe 100 gas elements, and you have 200 equations, and inverting them does not take any time at all. So, today the accuracy of the final result is not really sensitive to how you do the computation, but much more sensitive to how you calculate the properties. So, the emissivity of the gas, the emissivity of the surface, those are the inputs in which there is a large error. As indicated earlier, emissive surfaces is not that easily available, and it depends on the surface condition and the history. So, those numbers have a certain amount of inaccuracy unless you know the state of the surface accurately. So, the final accuracy of all this calculation is not sensitive to what technique you use here, but is much more sensitive to the accuracy of the input data. So, today in order to get a more accurate estimate of furnace efficiency, we need more accurate data input, and that is why the real challenge is not in the analysis part, that is all very well developed and settled, but it is much more sensitive to the kind of now, to give an example of a work done for a coal fired boiler. So, one example that is taken from published paper, they divided the boiler into 45 surface zones and 26 volume elements, and they estimated the amount of steam generated. So, measurement indicated the steam generated was around 627,000 pounds per hour. I am sorry about this British unit here, because that is work done for a British boiler. So, they give British units. Now, the question that we can ask now is, what are the estimates from the various models that have been used. The first model is the 0 dimension model of the kind we discussed in the last lecture, and we neglect soot, because soot is not easy to model. Then they get an answer of 354,000 pounds per hour. So, you can see the very large error in the 0 dimension model, almost half of the actual measurement. So, you may think that 0 dimension model is useless, because it is giving completely wrong answer. But if you take the same 0 dimension model and include soot and increase the emissivity of the gas, this number goes up slightly, but not much. Still, it is way beyond this number. Suppose you take into account the same model the fact that temperature is not equal at the exit, and do not include soot, you get an answer like 748. So, it is very clear that your estimate of the steam generation is very sensitive to what number you use as the exit temperature of the flue gas. And then you also account for exit temperature not being equal to gas temperature and include soot, number goes even higher. So, quite clearly the 0 dimension model either severely underestimates the steam generation, or it severely overestimates the steam generation. So, that means we need more. So, the next model is the long furnace model of the kind discussed. Long furnace model is really the model that we already discussed, and this is the model in which you have series of volumes, each of 0 dimension, and the gas slowly loses temperature as it goes up, and you solve this equation first, get the exit temperature, solve this equation, and so on in the vertical direction. So, this is a one dimensional model, which will definitely be more accurate than the 0 dimensional model, because it accounts for the variation of temperature along the path. And if we use a model without soot or convection, simplest case, you get 871,000 pounds per hour. On the other hand, if you include soot but no convection, then the number goes even higher. Then you decide not to include soot, but include convection. This number goes to 942. And finally, if you include both soot plus convection, the number again. So, all these numbers are a little too high. So, what this shows is that the one dimensional model really did not improve the accuracy of our estimate. It tended to routinely overestimate the steam generation. So, quite clearly we need to go to the full 3D model, which accounts for variation in the x, y and z direction. So, all the 3 dimensions you account for, the volume elements and so on. Then in this 3D model, if you have no soot and no convection, you get 531,000 pounds per hour. Then you have soot but no convection, it does go up to 651,000. Then let me not convert, let me explain this better. Not convection, because here is this is plus measured flow. You measure the flow and incorporate the convection transfer. Same here. Then you assume soot and assume a simple plug flow model, uniform velocity, you get 692. And finally, use a model with soot and assume the flow to be a free jet, which is what is true, because air coming from the fuel burner and taking in the primary secondary air will flow like a free jet. Then you get 650. And recall that measured value was 627. So, one can be quite satisfied that the prediction based on 3-dimensional model with soot and a free jet gives you a result accurate to 25 by 627, which is accurate to within 4%. So, this is quite impressive, but quite clearly you need a 3D model you need also either the measured or some estimate of the nature of the free jet that develops in the boiler. So, what we have seen from the 0 dimensional model to 3 dimensional model, you can see that if you want accuracy, you need to go to full 3 dimensional application. But if you want understanding, the best understanding comes from the 0 dimensional model of Hochschild, and it was really the building block for the development of the 3D model. So, we have given some idea about how furnaces are modeled in the real world, and how simple ideas that were discussed in the last lecture are useful to interpret the results of real furnaces. And as you pointed out, and if you want accurate information about the performance of furnace, you cannot hope to do so with a simple 0 dimensional model. 0 dimensional model serve the purpose of a tutorial. So, finally, the ideas from the 0 dimensional model were utilized in the 3 dimensional model to estimate the steam generated in the boiler to within about 4%. So, now we ask ourselves one of the issues we raised in this discussion. If you recall, in the calculation of emissivity of the gas in this model, we needed to use an empirical formulation about emissivity, because in a real furnace of 3 dimension, the emissivity depends upon the 3 dimensions, and we had not actually discussed how this should be done. So, let me discuss what is called the mean beam length. Mean beam length is a concept used by engineers to estimate the typical distance, effective distance in a 3 dimensional furnace that will give an accurate estimate of the emissivity of the gas. If it is simple parallel plates, the dimension of course is this length, but when you go to 3 dimensions, there are there is length and there is breadth and there is height, and we should know how we should combine these 3 length scale to get the effective length scale to be used for calculation of emissivity. We will write emissivity 1 minus A into LE. We must know what that LE is. Now, the way that is done is first to ask yourself if you can replace it by an equivalent hemisphere, and what is that radius hemisphere. So, mean beam length is that imaginary hemisphere of a radius LE, which gives the same radiation incident on the surface as a real 3 dimensional furnace. So, we would like to know the relation between this LE and all these dimensions of the furnace. So, first thing we do is to ask what is the radiation falling from a hemispherical furnace radiated to the wall. So, this will be nothing but and the volume element let us say small. So, we will call this as ds, and in the thin limit, optical thin limit, this can be written as, you expand this as 1 plus 1 minus a ds, substitute that, this becomes a, I am dealing with gray gas here, let me just write this as sigma Tg to the power of 4 by pi, and in this limit this becomes a ds into dA into d omega, and we will finally approximate this as 4, because this will give you a 4 pi. So, 4 will cancel out, dA ds is taken as dV, and integrate all volume will give you 4 V A sigma T to the power of 4. We will continue this derivation in the next lecture.